I hope you had a nice break. And without dragging on too long, I really appreciate that Bjarne decided to spend some time with us today and also prepared a presentation for you. So without further ado, Bjarne, please take the stage.
Okay, thank you.
Let's take my phone this time.
I really enjoyed Aaron's talk before. I mean, it's nice to see C++ being used for roughly what it was meant to be used for. That is, to use a language to allow you to express things under serious constraints of time and code space and compile times and compatibility issues, updating old code. So that's really nice to see. And I was particularly pleased to see him using template value arguments and concepts, which is something I've been pushing for and working for a very long time, many years. And so many people have told me that it's useless. So it's nice to have seen it proven otherwise. As a matter of fact, the talk I'm giving to you now, I've been writing aiming at people who are over-enthusiastic about languages for the wrong reasons. For languages being pretty and easy to say anything in, etc., as opposed to being a sharp tool for important, difficult, real problems. And so that's what I'm going to talk about here. If you think I am missing the target, send me an email. I am worrying that this talk is not aimed. It is not aimed solely at embedded systems developers, and it is not aimed thoroughly at sort of academic or language theoreticians, and it might fall between two stools. I'll try not to. Anyway, and it's always nice to be back in Aarhus. It's my hometown, and well, it's good to be here. I'm going to talk about C++ and constraint environments. Basically, that is C++ where there's constraints on something or other. It's not just writing a program to make it look pretty. There's constraints. I mean, constraint environment, well, that's the universe. That's a bit large. But, you know, they're running C++ on L2 on the telescope up there that took the picture. They're running it in the communication system that gets the pictures back. They're running it to render these pictures. So all of my pictures have something to do with C++. One of the things that I have had a problem with throughout my career is giving good demos if you're doing languages and compilers is really hard. The only thing the compiler ever tells you is you messed up again. I've always been envious about the robotics and the graphics people because they can give such great demos. At least I have some photographs here. Okay, so I'm talking a little bit about fundamental ideas and basic facilities. Then I'm talking about compile time evaluation, which could have led up to Aaron's talk, and core guidelines, how to get simplicity and safety more easily, and then a little bit about error handling and concurrency. It's a very broad topic, so I can't go in great depth, but I hope the breadth helps to see what C++ might be able to do for you. So basically, by a constraint environment, I mean something where there's constraints. And you see there, limited space for code and runtime support. Wow, that was your talk, right? And I did not write these slides after knowing what he was talking about. Limited data and space, limited processing power, unusual hardware, So this covers a whole wide variety of systems. And of course, not every system has every constraint. But when you think about languages and language design, you think about what breadth of areas you can actually cover. And the watch and the car there are both examples of a constraint system. They have very serious constraints on what can be done and how. And we're trying to help on the how. And the other thing that some people sometimes forget is that we never write a program in a language manual. We write it in an environment that has compilers, linkers, documentation, trainers, libraries, IDEs, emulators, you got it. There's so many things that we tend to forget when we talk about languages. And I sometimes find it very annoying when people compare two languages and they just write the number of lines of code on a screen or on a piece of paper, and they say, look, this one has fewer lines than that one, so it's better. But, you know, that's just the tip of the iceberg. It may be true and it may not be true. That's different. And yeah, it's have to remember this, and I'm going to talk mostly about language today, so you could see me making the mistake of everybody else also. But this is in the back of my mind when I work with language. And I'm going to try and attack some misconceptions. There's still a lot of people who think that the only way to learn C++ is to start learning C. This is just daft. You learn how to make all the mistakes, and then you should learn later how to fix them. No, start with something clean, and then if you have to go for compatibility or other reasons to the dirtier bit, then you do that later. And C is the best subset for constraint systems. If you really like to write assembly code, write assembler. I've made a living writing assembler at some point in my career, and I couldn't wait to get out of it. It was great fun, great intellectual challenge. It's even better than Sudoku, but it's not very productive. And so you need the tools of a better language to learn and to deliver things. And the other thing I am sometimes told is that to use C++, it must be because you have class hierarchies and a lot of free store allocation and deallocation, which you have to control very detailed. And no, there's better ways of doing most of these things. That's what you've got libraries for and language constructs. I'll get back to this. And also, to be reliable, you have to litter your code with runtime tests to catch all the errors. But you know, you will never catch all the errors. I mean, the last error is a joke. So we have to work better. We have to express our ideas more directly so that they can be checked by compilers and other tools.
I think maybe you lost your microphone.
Okay, it's back. Otherwise wave and I'll try and yell. I've also spent time as a professor, and one of the things you have to be able to do as a professor is to bellow. Okay, and also there's a lot of people that dislike exceptions. I think they're wrong. There's good reasons not to use exceptions. If you don't have more than, say, a kilobyte of memory, that's probably not the right solution. But if you have a megabyte, that's a different issue, and you've got room for it. Okay, so there's a different misconception. These misconceptions had to do with sticking to old stuff, things that was fashionable in the 70s. This one is the opposite mistake. To write code, you must use all the latest features all the time and nothing but the latest features. And if you look at YouTube, if you listen to a lot of people, that seems to be the idea. I don't quite get it. I mean, C++ is much better than C++ 98, but C++ 98 was actually pretty good, especially for its time, and C++ 11 was better 14 was better, etc. such. So the languages serve the programmer. You should just not be a language junkie. You should look at your problem, see what the language can help you get your job done, as opposed to try and see, ooh, there's this cool feature, how can I use it? Different logic. And basically, I'm not a fan of radical changes in code bases. They are very hard to do and they often fail. And so this idea that you go and you get the greatest new language and just rewrite all your code in it, all 10 million lines of it. I've never known this to work very well. I mean, there was a time where Java was going to absolutely kill C++ in 2 years. That was in '96. I was told that by executives from Sun. There are 5 million C++ programmers today, which is about 10 times more than then. There's also there's Java programmers. This is fine. I like programming languages in the plural. I don't believe in the idea that there's one language for everybody and everything. Okay, C++ should be good at what it's meant to be good at. The way you go about C++ at the most fundamental level is actually start designing your code so that it's tunable. Start with clean interfaces that are easy to use and safe. And then when you need to, you can sort of peel a layer off, go down one level, get more specific, more clever in details, use more about your hardware. If that's not enough, go down another level. Maybe you eventually get down to specialized hardware. You can do that. I mean, you can always peel off another layer. And this is why I call it the onion principle, because each time you peel off a layer, you cry more. You have to write more code, you can make more mistakes. But you don't start from the bottom at the lowest level, fiddling with every little byte and pointer and such that you can. That's where you get when you get all the way down to the mess when you have to. But really, if you write clean code, then you can maintain what you get, and the compiler might actually be able to understand what you did. I have as a rule of thumb these days, if I can understand the code, so can the compiler, and it'll probably run fast. So technically, C++ rests on two pillars. Always had a direct map to hardware, even unusual hardware, and zero overhead abstraction. Abstraction to get away from that hardware so that you don't have to fiddle at that level that's error-prone and unmaintainable, and in the limit slow. You have to get away from that level by having appropriate abstractions for what you're doing. Okay. When I say direct map to hardware, I mean that the instructions become, the operations become instructions, memory is memory, objects become things that are laying down in memory. You can see how you're doing it. You make higher level objects by simple concatenation. If you stick objects of the same type next to each other, well, you've got an array. If you stick them different types together, you have a struct or a class. And if you need something that changes, you can put in a pointer, which really is a typed memory address. This is the simplicity that has made C and C++ successful over the years. It is not clever. It is straightforward. It's an agreement between the programmer, the language designer, and the machine architect, and it's a very strong back to rest on. And you can use, as a rule of thumb, use a compact layout. There's the vector of point abstraction in C++, and I have 4 points there, and I get the structure up there labeled C++. It's a thingy that points to the objects, and there's 4 of them. And the stuff is usually laid out in FreeStore. Doesn't have to be, but that's what it usually is. So there's a memory overhead for allocating it, and then there's the stuff. It's fairly compact. If you go through object-oriented style, linked lists all over the place, then you get the mess over on the other side of this thing. And you'll see that is twice as much memory and twice as many indirections to get to the data. So the net effect is that it'll run 2.5 times, it'll take 2.5 times more to run. And so you can slow yourself down very dramatically by picking the wrong data structure. And sometimes the wrong data structure is the clever data structure with many indirections and such. I like fairly compact, simple data structures as my basis for what I'm doing. Okay, and the memory in C++ is the traditional thing. If you've been brought up with operating systems and old systems, this is trivial. This is the way it always was. This is the way Unix was laid out back in 72 and hasn't changed much since. This is the abstraction that underlies a lot of clever stuff below it. If you're doing embedded systems and such, you actually have to know what your memory is. This is the kind of slide that you can get bright students to find very unusual. I don't expect anybody here being particularly shocked by that one. I was shocked when I met somebody who didn't find it natural or obvious, and that's the way it has always been. But they had never been taught it, so that's it. And some applications may not use dynamic memory. Some applications don't have much stack. You have to have flexibility. You have to understand this. And if you need ROM, which a lot of people do, there's consts in the language that can be mapped over to ROM. Should be. It doesn't always in all tool chains, but that's what it's there for. Okay, so let's start getting away from that lower level. We have the direct map to hardware. How can we get away from it? And the obvious way to do it is to build our own types. And the most interesting and difficult types to get right is the simple types. From a language point of view, it's hard to get. In C++, we've done it. So there's a point. I can make a point. I can stick it where I want, in static memory, on the FreeStore, on the stack. And I can use it just like I use other types. One of my ideals for types is that I'll be able to use my type just as I will use an integer. If I use a big int, it should have the same scope rules, it should have the same overhead, same naming rules as the int in the language, or a complex number or whatever. They should change by their semantics, not by the syntax you use to express them. So basically, sometimes I say if you understand int and vector, you understand the basics of C++. That, by the way, used to be the biggest marine diesel engine in the world. And you can see the engineer at cylinder head number 5. And that has been on the seas for a decade. So if this kind of code didn't work, we would have seen it in the news. And therefore, it worked. Resource management has been key to my thoughts about C++ roughly forever. The idea for this came in the second week of working with C++ back in, 5 years before it was called C++, in 79. A resource is something you acquire, and then you have to give it back again. The idea is that you build up, when you create an object, you build up the environment where the member functions and other functions can operate in, and sometimes you require resources, and at the end of the lifetime of that object, those resources has to be given back again. And we know we are not actually good at giving things back. Ask any librarian. We take out books and we forget about it. And in computer systems, that means that the system grinds slowly to a halt as it runs out of something. File handles, memory, thread handles, or something like that, locks. So the resource release must be implicit and guaranteed, and for everything, not just memory, and predictable on prompt. And so, and I couldn't afford much runtime support, so none is required. That is the basis of much early C++ and central to a lot, probably most, current C++. That's called RAII, Resource Acquisition is Initialization, which is a wonderful term which proves I should not be in marketing. Basically, the idea here in C++, here's the vector. I have a user-defined type called vector, and it is templated. It has a parameter from runtime that is the element type t, and then I can make a vector of n elements, a vector of, given an initializer list to create it, and the destructor there is the key C++ feature. That's what cleans up whichever mess has been created during the lifetime of the vector. In particular, it'll clear up the resources acquired by the constructors. And here we have an example of lifting the level of abstraction. We have the implementation there, a pointer to some elements, some memory, and information about how many elements there are there. Very, very simple. It's simplified. In the standard, you can actually have the elements wherever you want them through having an allocator, but I won't go there. So basically, we get expressive code, complete type and resource safety, and optimal performance. There's an example there. I grab a vector of doubles with some well-known constants as the initializers, and I grab a vector of strings with some well-known language designers, and I create a pipeline of threads, named threads, and at the end of the scope, all of this goes away, implicitly guaranteed and right there. And it does recursively. If you do strings that are constructed from C-style strings, you have two levels of objects. A thread can be quite a complicated thing, and the cleanup is done. That's the key to a lot of C++, embedded, constrained, or general. It's the thing there. Now, here's an example that a lot of us will find familiar, and some will find half familiar. I was brought up with C in the old days, and I know what a union is. It's simply two elements that timeshare a location. It's either the one or the other. And a variant is something that is one of those, except there's a tag that tells you what is there, so that you can't make the mistake of, in this case, writing an integer and reading a string, which is going to be fatal at some point. You can't do that in the variant. Now, the reason for this slide is that I found that a lot of my students, when I teach them, has never heard of a union. And a lot of the old-style C programmers have never heard of a variant. So this makes it an example of how you lift the level of abstraction one level. You get greater safety, and the notation should have been better. Sometimes it is. Here it's so-so whether the notation is better for variants, but at least the assignment is more elegant. And basically, we need to get away from messy, error-prone code without having a massive overhead. There is a test here on the tag that says what's in this variant that there isn't in the unions, so the unions can run faster, and they can be slightly smaller, and they are far more error-prone. So There's a trade-off here, but it's good to know that there is. So one thing I like when I'm thinking about reliability is sometimes you can't afford everything. Or runtime checks, you can't express things precisely enough. But at least it should be possible to check it. The information should be available so that if you had a static checker or if you had somebody doing a code review, they should be able to know what the intent was and then see if there's a bug. With unions, it's very rare that you can actually be sure whether something is a bug or correct when you're looking at only one part of the program. Whereas once you have attached a type to the variant that says what are the alternatives, you can actually check it. So make the construct checkable even if you can't afford to guarantee checking every access. Furthermore, initialize everything as a first approximation. There's a lot of people trying to be clever of not initializing things till they know they need it. Well, why did you then declare it up there if you didn't have a value for it and you couldn't use it anyway? If you have a variable declared up here, you have a piece of code and you initialize it down there, well, no, you don't initialize, you assign to it, and somebody may use it in here and crash. The only really good reason I know to not initialize code is buffers. If you're having a large transmission buffer, having to initialize it and then fill it is a bit of a waste. And if you are in the kind of world where sometimes you have to count nanoseconds, you can tell the difference, though most code can't tell the difference. But buffers means that I cannot just say initialize everything all the time. Initialize everything almost all of the time. And you can afford it because you don't have to introduce the variable till you have a value for it. So it's the same. Bit manipulation. There's a lot of people that doesn't seem to like bit manipulation and languages that doesn't support it. It's messy, it's error prone, it can actually be expensive, but it's essential. You have to do it, and so therefore C++ for manipulating low-level things has bit fields, it has logical operators, and it has some library support for it. The point here is not so much anything to do with bit manipulation. It is just if something is necessary, we have to do it. Either that or we have to call another language to do it for us, which is a very popular solution in more academic languages. Or you can call assembly code for doing assembler for doing stuff that the language or the compiler has never heard of yet. There has to be a way of doing this, and there is. Okay, so use immutable data if you can. Especially in these days with a lot of concurrency, you can't have a race condition on a constant. And it's hard to beat simply reading a value. And it is really hard to corrupt ROM. Well, it can be done, but nothing is impossible. I have some very nice magnets, but it's much harder than RAM. So the language supports things like that. There's const values, there's const pointers, which is good for interfaces so that you don't mess with what is being referred to. Const extra and const eval functions are functions that can or must be evaluated at compile time. Aaron showed you how to do those things well. And const init is there to prevent runtime initialization, because sometimes the startup cost is too high. So if you can do the initialization through the linker or something like that, it's much faster and safer. Okay, so let's look at another little low-lying thing that people do in constraint systems that is a problem. Pointers. A pointer points to something into an array, but it doesn't know how many elements it points to. So if I have the standard interface that takes a pointer, here I pointed to an integer, and an integer n that is meant to illustrate how many elements there are being pointed to, then I have to check whether it's a null pointer. Then I have to, if I'm going to do p of 7, I have to check whether 7 is less than n, and hope n really is the number of elements. People forget things like that. And then you have to write a C-style loop with an explicit loop variable and write through all the elements. And again, what if n wasn't the number of elements, but the index of the last element, or something like that? Then you have a bug. It's hard to view. And if you give a too large value for n, boom, things go bad. We can do better than that. This is a major source of bugs and insecurities and such. It's a very trivial, boring thing, but it is a serious problem. So let's solve it. Span is a non-owning, potentially run-checked reference to n elements. So basically, I've taken the pointer and I've taken the n, the size, and put them into one type so that it is known by the compiler. And now, if I pass a span to a number of integers, I can test whether 7 is larger than the size, is less than the size, if the size is, that test is backwards. Okay, that's why you have code reviews. So anyway, I can test against the known size, and I can do a range for loop. Just give me all of the elements. I don't have to fiddle with index and sometimes get it wrong. And the information is available there. And now, if I have an array, I can just say pass f of a. It makes a span out of the array. It basically knows where a is and that there's 100 elements. The type system takes care of it. And if you want to have something that's different from all of the elements, you have to say so using a syntax. This gets the code reviewers looking immediately. It doesn't look naive anymore, innocent anymore. And so A of 5, yeah, it's fine. A of 101, that's the problem. You can still crash the system, but you have to work harder for it. So again, lift the level of abstraction. Don't lose performance. Don't add runtime overhead. As a matter of fact, a span can sometimes be implemented as just plain the pointer because the compiler knows what the size is, but in many cases it is simply the pointer plus the value stored. 2 values, just like we had to do before and always did. Dennis Ritchie wanted to add something like that, which he called a fat pointer to C back in the 80s. They wouldn't listen to him. They should have. He was a very smart guy. Okay, so one of the things I'm trying to do is to move things from runtime to compile time. If I can do things before startup, I can check it at compile time so the bugs doesn't happen later, and I don't have to have an error handler for it, and it'll tend to run faster. There's a whole lot of stuff that's been done in C++ that fits this pattern. Some is done by the compiler. Some is something you can do yourself, like constant expression evaluation and const expr functions. But the whole idea is get things away from runtime if you don't actually need to do it at runtime. Again, I was very happy to see Aaron's talk because this is exactly what he's doing. Therefore, he can test things and he can make it run fast. Here's an example. That integer square root was something I had requested by somebody in the Japanese embedded systems community. I don't know why they wanted some integer square roots. They said it had something to do with graphics and compile time. But anyway, if you can now put I square root of 9, or I square root of 2, 1, 2, 3, 4 into the code, instead of calculating the error on a doodle pad or in your head and sometimes getting it wrong. I mean, I'm sure I would get I square root of 9 right, but the other one. And anyway, if you saw the constant there, what do you think it meant? So again, if you can do it, it becomes, oh yeah, and then there's macros that are not typed properly, so there's holes in the type system. This kind of stuff is good. And as usual, we want to lift the amount of work, the level of abstraction a little bit. And so there's some examples from Chrono to show that it's not just for built-in type compile time evaluation. It follows the rest of the C++ in lifting the abstraction level. So there I want to output the weekday of June 21, 2016. And it's a Tuesday. And that's what it'll say. It'll actually calculate that weekday at compile time and simply inject into the code cout Tuesday. And the way I can see that happening is I have a static assertion that says, please check that weekday June 21, 2016 is a Thursday. If it isn't Tuesday, if it isn't, that program will not compile. This is a very useful feature when you are writing code that makes assumptions about things like the hardware sizes or availability of features. You can test that. And here it's tested. And well, it's a compile time test. There's no runtime code here. And so I can write code using this. I'm using the system clock, outputting it, and writing output out with a time zone. All of this stuff is standard now and saves us a lot of bother. I don't know about in your environment, but in the financial world, there's a lot of dates and a lot of times and a lot of fine-grained times, and people have a hard time getting this right. Once you have things from nanoseconds to years and time zones all over the world, and leap years and leap seconds and all kinds of good things, this is where you want a standard library. And it's nice to know that standard library is about faster than anything else I've seen for time. And I've seen a fair bit. The output was there. The output of TP, it's that string. Okay. And a lot of the compile time computation becomes invisible. So I have provided some suffixes there, user-defined suffixes, I for imaginary, min for minutes, s for seconds. The durations there are in the standard library. So is I, by the way. And we can get C++ style strings with the suffix s. And the implementation of that is not rocket science. It's down on the last three lines. You don't have to write those because it's in the standard library, but if you wanted to, and if you wanted to have your own units in some system, that's how you can do it, one-liners. And the compiler will then pick it up with literals, with suffixes to get the meaning right. I've seen enough slightly wrong constants in my in code to know this is valuable. It makes it easier to read. It makes it harder to make mistakes. Okay, so back to this thing about how to get code safe and easier to write. One of the problems with C++, as with any long-term successful language, is it has some barnacles. It has some old stuff that you would rather not see, but you need because there's a billion lines of code using it. Can't get rid of this old stuff. So how can we get further? You must separate the idea of what is legal in the language so that the 20-year-old code running that diesel engine will still run, and modern stuff that you would like to write and you would like to better check. And so we try to separate those two things. What is legal and what's good is not the same thing. And we want to lift this up. This is known as the C++ core guidelines. Type it into GitHub and you will find the rules there. There's a couple of books out explaining it, came out this year, that's explaining it, so it's getting some traction. And basically the idea is that we specify what we think modern good C++ is, and then try not to write the rest. That simplifies the world. And it has a coherent philosophy. You can read it in the stuff on GitHub. And it's not just a collection of fashionable rules or such. We're trying rather hard to really say what is the right thing to do with C++ today. Not quite today, we're only up to 17, but C++ 17, but we're getting there. The philosophy is not just ban anything that's bad, because if you do, you find you can't write any code. If you are not allowed to use any raw pointers and arrays, how would you build a vector or your own data structure? You can't do that. So the philosophy is, first you extend the language with a more appropriate base. That's part of the standard library, and it's part of what is known as a guideline support library, which is about 10 classes, and they're small. And we want to put them out of business. Span started in the GSL. It is still there. It was put into the standard. So we want to be put out of business. But the idea is extend, and once you have extended it, you can cut away the low-level stuff that you don't actually need. Furthermore, you can do this gradually, adopting some rules and not others. So there are people who adopt the rules for getting the memory safety, for instance, and don't adopt all the style rules. And basically, it's being maintained. I had a meeting about it this week on the web. It's not something that was done and put on the web to die. We're working on it. Each rule has a name, a rationale, so that you are told why somebody thinks you should follow the rules, examples, good and bad, and notes. And if it is one of these rules that says don't do that, there should also be a rule that says what you do instead. So it says don't have ownership pointers. That is, a raw pointer is not an owner. So what do you do instead? You use unique pointer or shared pointer, or there's some annotation in the core guidelines if you want to go lower. Basically, what do you do when you want to implement a unique pointer? Somebody has to do that. So, and enforcement suggestions so that people can write static analyzers that checks that you follow the rules. My idea is that you start up, you set up a set of rules you want checked, and the checker, whenever it finds one, dumps you into the right paragraph in the core guidelines that tells you why you're supposed to do that, what happens if you don't, what can you do instead, that kind of stuff. And so given that, you can write type and resource safe C++. No leaks, no memory corruption, no garbage collector. I'm not a fan of garbage collectors. They are unpredictable, take up a lot of memory, take up a lot of time. You can, in some applications, do a really good job using them, but for what I care most about, it's not the right answer. No limitations on expressibility. We don't want some subset of C++ that cannot run fast or takes up a lot of runtime support. No performance degradation, and it's ISO C++. I don't want to design another language. It is hard work for a long time. Once is enough. So here's an example, void f there. I allocate a new, just a new x of whatever x is, and I take a local variable x. I take a unique pointer to an x, and the static analyzer, you can do it on Visual Studio. It has an analyzer that will do this. Some of it is done on Clang Tidy. I haven't tried it lately, so I don't know if it catches this one. But first of all, it says there's a naked new there. It's an owner pointer that comes out of the new. You must delete it, but nobody knows that. It's just an ordinary pointer. So the core guideline checker complains, and the violation at the end says that you leaked PX. Now, the solution for this kind of problem is to use local variables, like that little x there, or ownership pointers, like unique pointer. We need tool enforcements for this, because it's just too hard to follow a bunch of rules. And there's things compilers are much better at, like keeping track of where names go and what comes in and out of a function. We have to aim for good use of pointers in array. We aim for safe use, be explicit about ownership, use Raii, and make sure that the pointer is potentially valid, which means that we have to eliminate dangling pointers, and we have to enforce invalidation. That is, if you delete something pointed to, that pointer should not be valid anymore. If a pointer goes out of scope, it's not valid anymore. And we have to do some runtime checking. There's some things that you can only do with runtime checking, like checking for null pointers and do a range check. That's what span is for. And here's an example of statically preventing dangling pointers. As I said, there's a function, and I'm trying to return various pointers there. I return the address of a local variable. Not a good idea, and even the compiler can figure that out, but so can the static analyzer. It's all right to return a pointer to something that's static, because that doesn't have a lifetime limit on it. Return something to new that's newed on the free store is okay, but it's not okay to throw away the information that that value owns something. It's supposed to delete it. So it's all right from a scope, from a lifetime point of view. It is not okay from a management of new and delete point of view. And then finally, I got P in from the outside. Therefore, it must still be valid when I come back to where whoever called me. So those are the three kinds of things that can come out of a function. Something over to free store, something to static, and something to that came in to the pointer. And this is part of how the static analyzer works. And then there is the problem of returning pointers to things that exist in your own memory somewhere. So here is a vector. A vector maintains somewhere over on the free store an amount of data that holds the elements. And there's a pushback operation here that extends the vector with one element, and that's fine. Except, of course, when you expand something, you may actually have to move it to make room at the end. So potentially, when I ask to push back 9, it has to grow from here to there. What if there's no space there? Then you copy it over here with more space and move elements over there. Which means that if I'd done what I just did in G below, I took a pointer to an element. Then I went through some functions, did a pushback, moved all the elements. That pointer now points into the old data. Mustn't happen. You can statically check that this has happened, and this piece of code will be caught. If you don't have a checker, this code passes the compiler and your system will crash if you're lucky. If you're not lucky, it'll give you a bad result. I prefer crashes mostly, except for real-time control systems, but that's a different issue. But basically, this can be statically done. And so if you invent these two slides combined will take care of most, in principle all, and in practice most, memory issues. So basically, never let a pointer point to an out of scope or deleted object. And we basically know how to do that. And this is not just pointers. It's any way of getting an address to escape. So throws, returns, placed in containers, bound into lambdas and such. I once thought I could break the checker by having a local variable bound into a lambda and then pass the lambda back as a value. You can see the problem here. I'm returning something that contains something that points back into the stack frame. Well, the checker got me. And this was a couple of years ago. It's better today. It's hard to cheat. Okay, invalidation is conservative. I'm wondering about getting it's something for more fine-grained let thing. But we're working on this. So this belongs together with constraint systems, embedded systems, because we don't want to have big systems for keeping track of our data. This kind of stuff is cheap. It is predictable, and safety is often a concern in embedded and constrained systems. Those pictures of spaceships and things like that, cars and such, that I worry about those. That can be done. Okay, potential runtime errors. We can check. We have a type in the GSL called not null. If you assign a pointer to it, it'll check whether it's null and throw an exception if it isn't. If it is null, but after that you can use not null without ever checking again. So you save a whole bunch of tests against null. If you're going through a series of 50 checks, 50 calls, you might end up with 50 checks. That's not good. That's expensive. Code space also. On the other hand, if you don't check all of these, you might actually get a null pointer in somewhere. With not null, that problem is solved. And we have span for dealing with the range checking. And basically, the idea is to keep code simple. And I mentioned initialization, loops, the range for loops, control structures, data structures. Don't be too clever. And try and use things that are not error prone. I have for many years refused to teach do, because I've seen it far too often that the precondition is not held. And then somebody sent me this slide. That's I like it. So use constructs that are naturally resilient against errors, as opposed to whatever is the convenient, obvious, minimal solution for every single thing. And so basically, can core guidelines ensure safety? And basically, yes, for most definitions of safety. And one of the things that I have observed is that there's many definitions of safety. Depends on your context and such, needs further work. We're working on something called profiles, so you can define a set of tests that is being done, so that you get a guarantee that that set of tests is done correctly, and the rest of them, maybe you can't do that yet. Maybe your code base has too many old constructs in it or something, but you can do it. And we need static analyzer support, more of it than is available now. Error handling. This is one of the hottest debated topics I ever see. You've already got my first answer, which is if you can get the compiler to check it for you, you don't get into the discussion between whether you have an error code or an exception, and if so, how is the error code expressed in the language. There's at least a dozen different ways of dealing with errors that are fundamentally an error code being passed along. And so different domains have different requirements, different kind of errors. And one thing I find is that a lot of people are very, very certain about themselves in this. They know the right way. If you just did error handling just the way they did, you would be happy and there wouldn't be any problems. The problem is there's lots of people like that, and they don't agree. And I have never found a single solution that are correct for all errors. So, first of all, try and be specific about what it is you want with your error handling. That is, for a system, have a strategy, have a policy for how you deal with errors that are not handled locally. I'm not talking about errors handled locally. If statements are very good for that. I am worried about things that happen there and has to percolate up there. There's a lot of errors of that kind in a lot of systems. Again, may or may not be a common thing in your system, but there are systems there are. And so we want simple code, efficient code. We want to avoid leaks, and we want to make sure that any error that is handled is detected, is eventually happened. This is hard to do in general, and the alternatives for errors that can't be handled locally is the main discussion point, and has been for 50 years. Return an error code is one way of getting an error out of a function. Throwing an exception is another one, or you can just terminate, saying, I'm not dealing with non-local errors. We'll terminate. There are systems that are done like that. Think about a lot of stuff on a fighter plane. It has to be resilient against bullets going through one of the processors anyway, so anything fancy will not work. That's a dramatic thing, but say if you're a server farm with 80,000 processors, you're going to have a processor die every day anyway, so you have to be prepared to deal with it. On the other hand, there are rules, sometimes legal, sometimes practical, for some systems that simply mustn't crash, at least not without writing a report first or something like that, so you can't use terminate in all cases. Also, if you don't have 80,000 processors, but only one, you better try and recover for errors. So the point here is that there's a huge domain of things that can be done. And error handling is the hardest part of code to write, because you know you're in a mess when you get into the error handler. So now you have to write code where something else already failed, so what can you trust? I hate writing error handlers. Sometimes it's half of the code of a system, and it can dominate code size. Oh well, fine. Error handling cost. A rare error on a long path from detection to handler, use an exception. They're very good at percolating an error, say 50 levels up. If frequent errors happen and there's a short path from the detection to the error codes are faster. And so the way I think about it is that for exceptional things, that's what exceptions are for, the non-error part is very fast for exceptions, and the error part is dramatically slow sometimes. If you want quick recovery from the errors, it's probably not right to have an exception, But especially if the error and the error detection and the error handler are close to each other. And so for error codes, it tests both non-error, it tests on both non-error and error return paths. So you have a cost every time you go up one level. Exceptions only have a cost when you go up the bad path. And so there's a cost everywhere. And in increased cost of returning a value, you have to return an error code. Now, you can embed the error code in something like pointer and non-pointer, but that has other problems. In general, you get more stuff that has to be passed back up, and you have to test it. Termination is dirt cheap if you can afford terminating for anything that can't be handled locally. I haven't written all that many programs that does that, but I know people do that for a living. Again, not everybody has your problems or mine. Okay, so throw an exception when you need a guarantee that all errors are handled, all detected errors are handled. Notice that if you have to write if then else statements or switch statements, sooner or later you forget to test one. When did you last test the result of printf? It returns an error code. It is quite possible for a print statement to fail, especially if you have a network in between you and where it's printed to. It happens. I have never seen a program that got anywhere near close to testing printf consistently, which meant that that program would, if put on a network, eventually crash. If you want guarantees, exceptions are better at it, because you can't actually, if you forget if you don't catch an exception, it goes into the exception handler. It goes to, the termination, and that's what it's meant to. It'll happen in testing or something. That's guaranteed to dealt with. If an error must percolate back up a call chain a long way, exceptions are good at that. If there's no suitable return paths for error code, how can you use an error code? If I say x equals y plus z, where's the room for the error code? You would have to rewrite your code to a function that took 3 arguments so that there was place for an error code to come back. How about a constructor? There are places where it's very hard to use error code. And the other thing is that if you have a complicated function with many possible error codes and where you have to combine the errors to find where you send things back from the complicated code, exceptions will deal with that. Error code, you have to write the code that correctly collects all the errors and combine them in such a way that you can return them properly. I find that that is error prone. And so, by the way, for people who have not used exceptions for real or in Java or something, don't litter your code with try-catch codes. This is what Raii is for. You embed that information inside objects so that the destructors will throw the exception if something's wrong. Or if the exception is thrown, the destructor doesn't throw the exception. The destructor is fired when the exception passes by, so it's all cleared up normally. Don't ever have a destructor throw an exception. Don't. There are ways to avoid that too. Okay. But try-catch statements, if there's a lot of them, a naked try-catch statement is about as popular with me as a naked new. It's not the way you write good code. Return an error indicator, an error code, when the failure is normal and expected. If I'm opening a file, yeah, I should expect it won't open. It might not be there. If I am going through a loop. If I want to escape from the loop, I wouldn't throw an exception. There's nothing exceptional if the logic of the loop says that it can break halfway through. That's what error codes are for, and local control structures. And another criteria for using an error code is that the immediate caller can reasonably be expected to handle that failure. If you have to percolate a long way, exceptions are the way to go, not repeatedly having to remember to pass that error code around and combine it with any other errors that happen on the way up. And well, you better stick with return code if your code is already a million lines mess of old pointers pointing all over the place and no strategy for resource management. And the other thing that I find is sometimes if you have a set of parallel tasks and you need to know which of the tasks had the error, throwing a plain exception is not always a good idea, not unless you embed inside the exception some code that says where you came from, which is the same as an error code. So there's a place there. And okay. And don't try and percolate every error to a handler. Okay, that's with error codes, trying to go on the way. Okay, so exceptions rely on Raii, and there's a somewhat messy example. Try writing this with error codes and make sure you get all of the errors handled correctly. There's nested allocations, there are threads. Okay, this is just an idea. How much time do I have? Am I running out?
We have 20 minutes left, including questions.
Including questions. I am going to finish in 5 minutes. Okay, so we have concurrency, and that's a major issue in many constraint systems, because many constraint systems need reliability, and you get reliability with multiple computers, multiple processors. And so there's a whole set of things in C++ that supports that directly. It's got a memory model. That means that memory behaves roughly the way you would expect, lock-free programming, atomics, threads and locks, just like pthreads or in Microsoft threads, except that they're type safe and standard and portable. And parallel algorithms, coroutines. I cannot do this all. I'll just show you this little example, which came as a surprise to me when I first saw it. When you write code, if you share data, you have to avoid data races. A data race is when two threads read and write the same data. Now you don't know who got there first. It's one way of defining it. And so here I have a piece of innocent looking code. The only problem is that there can be an async change of X from some other thread in between testing that there's only 3 cases for X and doing the switch. This is actually a famous security breach, because you inject an asynchronous change after X has been tested, and then you switch with a value of X that is now different so that you get to the right place. You have there a free go-to in your program. And okay, so you have to run this a million times before you hit the jackpot and it happens, but then you're in. And there's a lot of things that happens a lot of times. So don't share data if you can help it. And if you have to share data, be sure you use your logging correctly. Here's what you can do at the very lowest level. Compare and swap operations. The expert advice is leave this to the experts. I once was an expert. I wouldn't let me try to do it today in real production code because you're not an expert if you're not do it almost full time. So serious, but that's if you want to go low, if you want to have to implement locks and threads, you need something like this. The next double thread initialization, if you have seen this in various languages, in C++ it now works provided the initx is atomic. Atomic is really the cheapest interlock mechanism you can get, and you can use that to protect more expensive tests like lock guards and such. And you can also use mutexes, which is the way a lot of the stuff is done. Here I have an example of two mutexes, each protecting some shared data, and I need to get to both shared data. The simplest example I had there, just S1 plus equals S2. And there's a facility in the standard library, scoped lock, that will grab you a set of locks. It will not pass there till it's got all of the locks, and it will not take half of the locks and sit waiting for the others to come along, because if that happened, you had the classical deadlock, right? Thread 1 gets M1, thread 2 gets M2, and now we are stuck forever. This cannot happen. Scope locked will get both or none. Passing results around there. Fine. Okay, I promised in 5 minutes, so I'm getting here. Here's a summary of the foundation of the C++ language. We have a static type system. It has uniform support, equal support for user-defined and built-in types. So the types you build, you can build them as good as the one Dennis invented, Dennis Ritchie. And there's value of reference semantics. Value semantics is nice and clean and sometimes too expensive, so you need to implement it with, say, reference semantic. We have Raii, systematic and general resource management, object-oriented programming, generic programming, compile-time programming, and direct use of machine and operating system resources. That's sort of the key. And so if you want to use modern C++, it means the recent stuff. You can find talks, there are books, there are the core guidelines to help. And if you're looking at modern stuff, look for modules, look for concepts, and look for concurrency. And don't go hog wild on language features. Choose the language features that solves problems for you, not just because somebody gave a talk or wrote an article saying it was cool. And don't be too clever. I really think that we should be clever solving our problems, not expressing the solution to our problem. It's too much clever code. Quite often it gets so complicated that the compiler can't solve it. I have speeded up systems over the last few years by ripping out all the clever code first and seeing if it ran as fast. Quite often it ran faster. So try not to be too clever. And there's the summary of C++ for the last 40-some years. Okay, questions?
Thank you. Questions? All right. There you go.
A few years back, I saw a talk titled Garbage In, Garbage Out, which I think really hit a spot about where he talked about runtime checking data, where he was talking about, well, you gave me the wrong value for using in this method. Why should I error check it for you in runtime and waste cycles for it?
I do very little checking of arguments to call. I do a lot of checking at the edge of the system, making sure that the data is checked, as opposed to the argument. If you want to check arguments, you are on a quest to test everything under every consistent or every situation inside the system. And how did you get to this function? So what should you check, or what can you take for granted? I think that is a loser. So I focus on checking on inputs. I use insanity checks in case of my hardware has done bad things. And then I do range checking and null pointer checking. Is a good summary.
Okay.
Push it to the edge of the system.
Yeah, thank you.
And again, that's the kind of systems I have experiments with. Other people might have other additional concerns.
Hi, so I've been working to introduce coroutines to the Roku world, and I was wondering if you have any thoughts on what we might expect from future standard library releases in terms of higher level abstractions, or also any open source libraries that you're aware of that might be production ready.
We could get the coroutines, but not enough standard library support to make them easy to use. I was sad about that. As I said, we wouldn't be here if it hadn't been for coroutines. They were what kept C++ going throughout the 80s, because we could do things faster than anybody else. Now, what can we do now? In C++ 23, we will get generator, so that you can get things that generates a sequence of values to drive a use. And we may get task that does that asynchronously. We won't get much further, unfortunately. We had great plans, and then COVID hit. And there is a library out there, Coro, from Facebook, which is actually pretty good.
Thank you.
And it's available open source.
Yeah, it's just a follow-up question to the previous answer. When you say edge of the system, how do you define that?
I couldn't hear you.
Sorry. It's a follow-up question. What do you define as the edge of the system? Is it
The edge of the system.
The edge of the system, yes. Yeah. It's where the data is coming in from inputs. I mean, it could be stuff coming in from the web, or basically test your data sets as they're coming in. Test your requirements. Don't just fire up say a printf format or a SQL query without testing it. If you have a precondition that all of your values are positive, check it. But I was thinking about things like SQL injection.
Thank you.
In other words, things that weren't yours, so you couldn't test it in advance.
So, going on the coroutine and the async stuff, now that there aren't all that many questions, could I just get any thoughts you might have on the stuff that on executors that Eric Niebler and company have been doing?
Oh dear. I have been waiting for executors for many years. I've been in meetings with it. I have twice thought we had consensus on a model of executors. Let's say I'm still hopeful, but I'm also very tired of waiting. They keep changing the model, keep changing, get a bright idea, and then everything's thrown away. I would have been very angry if it wasn't that the ASIO library wasn't available for the kind of networking I have been needing to do, and has been very good, and it has gone through standardization. It's just never been improved, but I can download the version we would have voted in if we had had it. But we didn't have that networking because the executors, that is the general model of asynchrony, didn't get finished. Currently, there's some debates about how errors percolate through from senders to receivers. It should have been settled some time ago, but as I said, people keep getting a better idea. You know Voltaire, the best is the enemy of the good.
It's just a little bonus question that I always wanted to ask after I saw Jason Turner's with const everything. That if you had the opportunity to go back and change that, instead of we having const, we have a mutable keyword, if you would have done it.
Okay, this is the time machine question. And there are several aspects of that. First of all, we don't have a time machine. Secondly, if we had a time machine, could, say, vintage 1990 Bjarne have done it? Could he have understood the solution? Could he have seen the problem? Did he have the resources that it allowed it to be done? The big machines in those days had 1 megabyte of memory and 1 megahertz. And furthermore, the problems have changed since. Things like default of const or default of virtual and things like that are extremely hard to change. People talk about changing defaults. That doesn't work because now you have to look at a piece of code and guess which version it was written in. So defaults you have to get right from day one. If you don't have defaults, you're getting what we are getting too much of now is endless annotations for saying everything explicitly, which is a right royal pain in the neck, and people get it wrong. If you have to write 7 things on a type, that's not good. So if I'd had a time machine, I would have changed the syntax of C and C++ a bit. So you need the time machine to go and explain to Dennis that he should wait half a year till they invent better grammars, better parsers, because that's how we got the strange syntax. For me, I would also like to have no conversions. The two-way conversions between the built-in types is just a pain, especially the signed and unsigned ones. And then finally, for myself, if you got the time machine, got back and got to me in about 87 and explained concepts to me, I could have done it, and I knew the problem. But no time traveler came.
All right, we have a few questions, several questions online, but we'll pick a few and Aaron's volunteered to ask them.
So what was C++ called before it was called C++?
C++ was initially called C with classes, because that's what it was. I'd added classes to C. Then I was asked to rename it because people started calling it C. And that was creating a certain amount of confusion. And there's people who claimed that it was insulting to Dennis, but Dennis didn't think so, so that wasn't the problem, despite you find that in various stories and history books. Dennis and I had lunch most days for 16 years, and I'm still friends with Brian Kernighan. The C++ wars is not among the principles. After that, I then had to pick a name, and I thought C84 would be a really nice name. I'm not good at naming, okay, but I thought that. The people from the ANSI committee came back and said, you can't do that. It would be too bad if that happen because in 85 we are going to get the C standard, and that will be referred to as C85, and it will be very embarrassing if C84 is a superset of C85. And so I had a competition with people, and we got C++.
Okay. During the exposition of error handling, you didn't, you never brought up the expected type, the standard expected.
There are a bunch of types to make error codes more easily used. The ones I like are the ones that throw an exception if you forget to handle them. But they don't please the people who don't want any exceptions, which is fine if it's because of small memory. If it's just because they're panicked because it's not visible, I'm not so sympathetic. But if you had to have error codes, an error code that falls back to an exception if you forget to test it is a good idea. And I've forgotten which one it is that's called like that.
Okay.
There's about 8 proposals of various sorts coming along for how to do that problem. It's amusing because one of the reasons I did exceptions was to lower the number of error handling techniques that was in use at the time. There was only about 4.
All right, we have time for one more question. Do we have one online, Aaron, or?
Yeah, okay, I'll ask it anyway. Someone wants to know your opinion on carbon.
Yeah, bubbly drinks are nice. Anyway, I'm not too keen on commenting on carbon. It is very, very unspecified or underspecified. It's of a lot of stuff. We'll have something like this. Like C++ doesn't have a package manager. That's horrible. Therefore, we need a new language. And we think we'll get a package manager next year, but we don't know what it looks like. I mean, you can't comment on things like that. They have concepts that are not the concepts of C++. They have modules that are not the same as modules in C++, and they don't have coroutines. They're just starting out. Give them a couple of years, maybe it'll become interesting.
All right. Well, thank you very much for the presentation. And also just as an appreciation, you did share with me that you do have some vices, one of them being wet wine. So thank you a lot for your presentation and coming here today. Let's give Bjarne a warm applause.
Thank you.